First question here. We have a classroom with 14 boys and 16 girls. 2 of the boys have glasses. First one. What is the probability of picking a boy? So, the probability of picking a boy. We want the number of boys over the total number of people. So we have 14 boys and 16 girls. So in total, we're going to have 30 students. So the probability of picking a boy will be 14 over 30. And if you get that as a percentage, it'll be what? It's the same as 7 over 15. And that's equal to 46.66%. You can leave it as a decimal, or you can write it as a percentage. Either or, same thing. So that's how you do the first part. Then the second part's a bit trickier. What is the probability of picking exactly one boy and 2 girls? Okay. So we're going to be using combinations here. Remember, if we want to pick one boy, that means we're going to do out of 14 boys, we choose one. So on your calculator, it'll be what? 14C1, something like that. They're the same thing. So we want one boy, but then we also want to pick 2 girls. And they don't we want to pick 2 girls. We can't just say there's 16 girls. So we pick one of the 16 and then another one of the remaining 15. We have to use combinations here because we can pick any 2 girls. So then out of the 16 girls, we're choosing 2, or in your calculator, you'll write 16, choose 2. Then we have to divide that by the total number of combinations we can make out of picking any random 3 people. So in total, if we were to pick 3 random people, we would have 30 choose 3. So that's how many total combinations of 3 people we could get. But we want 1 boy and 2 girls. So our probability of picking boy, girl, girl, we'll say, or that could be boy, girl, boy, or girl, boy, girl, or girl, girl, boy. I can't speak. You know what I mean. It's any combination of 2 girls and a boy. So that's going to be 14, choose 1, times 16, choose 2, all divided by the total number of possible combinations, like this. And when you put that into your calculator, you will get, so that is going to equal 12 over 29, and that is the same as 41.38%. So either the fraction or the decimal again. That one was pretty tricky though. Then the last question is, given a boy is chosen, what's the probability he's wearing glasses or he has glasses? So we have probability of glasses given that it's a boy. So what's the probability of being a boy? There's 14 boys. So we're given it's a boy. So we're only considering the 14 boys. Then we have, how many have glasses? 2 of them. So the probability is going to be 2 over 14, which is the same as 1 over 7, which as a percentage will be 14.29%. Boom. So that's the answer to the last one. This question here, we have traffic lights can be green, amber, or red. If I pass by 6 traffic lights on my way to work, how many different arrangements might I see? Like you could have red, green, green, amber, red, amber, whatever. So it's the first color you see when you approach the traffic light. How many arrangements could we have? Well, okay, think about it. The first traffic light could be 3 colors. It could be green, amber, or red. The second one could also have 3 colors. Green, amber, or red. Same with the third, same with the fourth, same with the fifth, same with the sixth. So that's equal to 3 to the power of 6. And that is equal to 729. So there's 729 different arrangements of colors you might see on your way to work. Then, if the first light you see is green, and the last light I see is anything but green, how many, that's a typo, how many combinations can I see then? So, again, just write them out. The first light you see is green, okay? So that's just one color. Hang on, is that right? Yeah, that's one color. Then, the last one you see is anything but green, and the middle what? 4 can be any color. So the middle 4 can be either green, amber, or red. And then the last one you see is anything but green. So that's only 2. You can have either amber or red. So now we're just going to put this into our calculator. So 3 times 3 times 3 times 3 times 1 times 2. That's 162. So there's 162 different arrangements you could have there, where the first light has to be green. That's why we have a 1. and the last light has to be anything but green. So that's why we have a 2. If no consecutive lights are the same color, how many combinations could I see? Now, think about it again. So no consecutive lights can have the same color. So the first one can be any of the 3. The second one can't be what the first one was. Say if the first one was green, the second one would have to be amber or red. Then the third one, well, if the second one had to be amber or red, then the next one has to be either green or the one that wasn't chosen from before. So say it was green, then amber. This one could be green or red. So we're gonna have another 2, and then you're gonna have another 2, then another 2, and then another 2. So 1, 2, 3, 4, 5, 6. Perfect. So put that into the calculator. 2 times 2 times 2 times 2 times 2 times 3. That's 96. Boom. Done. Now, okay, perfect. Bernoulli. Okay, we have 1 in 5 students say that they hate French. If we ask 10 students, what is the probability exactly one of them hates French? What's this going to be? This is Bernoulli's trials, because we have a probability that they hate French, so the probability that they don't hate French is just 4 over 5. Only 2 of these outcomes, either they hate French or they don't, and one person hating French doesn't impact the other person's opinion of French. So we can use Bernoulli's trials. So remember, probability that one of them hates French is going to be, so out of 10 students, one of them hates French. The probability that they hate French is 1 in 5. So that's 1 in 5 to the power of 1. That means that we have 4 over 5 times, what was it, 10 minus 1? So there's just going to be 9 up here. I should have wrote up here. It's in the notes anyway, but the probability is equal to n choose r, then we have p to the power of r, and then q to the power of n minus r. Like that, where p is one probability, and then q is just like 1 minus p. So when we plug that into our calculator, we'll get, so that's going to be 0.268, or 26.8%. That's the probability that out of 10 kids, only one of them hates French. Then the second question, it says, we asked a group of students, and the probability that they all hated French was this. Long decimal. How many students did we ask? Okay, this is again Bernoulli's trials. We don't know how many students they asked, but we know the probability. So it's what? 0.00012345256. So that's going to be, they asked some number of students. All of them hated French. So we'll just assume they asked n students. They all hated French. So out of n students, n of them hated French. The probability that they hate French is 1 over 5. That's to the power of n, because they all hated French. And then we're going to have 4 over 5 to the power of n minus n, which is just 0. Anything to the power of 0 is just 1. And if you plug it into your calculator, say if I assumed n was 15. If you did 15, choose 15 in your calculator, you're just going to get 1 here as well. So both of these are just 1. That means that this long decimal, I'm not going to rewrite it, is equal to 1 over 5 to the power of n. Then, if we use the rules of logs, we can get that the log, or we can do natural log actually, the natural log of the long decimal is equal to n times, because we can bring it to the front, the natural log of 1 over 5. That means that n is equal to the natural log of the long decimal divided by the natural log of 1 over 5. And just plug that into your calculator. So when you plug that into your calculator, you should get n equals 8. So we asked 8 students, all 8 of them hated French, and that's how we got that probability there. If you ever wanted to check, you could just do this filling in 8, and you should get that probability. Now, the probability that a person wins a slot machine is 1 in 10. The cost of each game is 50 cents. How many times will a player expect to win in 90 plays? So the number of games they expect to win, E, should be the number of times they play, 90, times the probability that they win. So that's going to be 9. So they will expect to win 9 games if they play 90. Then, if the machine pays €2 for every win, how much money do they win if they play? And would they expect to win? Expect is the key word there. How much could the player win in 90 plays? That means we're going to say it's €2 for every win, but they expect to win 9 times. So they should win €18 if they play 90 times. And then C is saying, would they make a profit? Would they make a profit? Well, if they're playing 90 times, and each time they play, it costs them 50 cents. Okay? Or €0.5. That would equal €45. So they spent €45 on the game, but they would expect to win back €18. So that would end up being a loss, because if we do 45 minus 18, that's going to be €27. So they paid €45, but they got 18 back. So they lost €27 in this game. So this isn't a fair game. They shouldn't have played this game. A little note on this question. So if we were to get the expected value of this game, the EV would be the probability that you win is 1/5. Or what? Was it 1/5? No, it's 1/10. Even worse. So the probability that you would win the game is 1/10. And if you won the game, you're getting €2 back. And then if you don't win the game, that's the other 9 out of 10, you get 0 back. So that's just going to cancel. That means the expected value of the game is 2/10. That's equal to 1/5, or just 0.2. So on average, if you play the game, you should expect to get 20 cents back. But notice it cost 50 cents to play. Cost 50 cents, so 0.5, which is greater than 0.2, the amount you're expected to get back. So you shouldn't play. You shouldn't play because the expected value is below the cost to play. And we proved that here in the actual question itself. If you play 90 times, we said you're expected to win €18, but you paid 45 for those 90 games. So it's not fair.